Okay, good morning, everybody. So this is the next section. I'm going to go through design for fabrication. My name is Douglas Mair. I'm one of the professional officers at ANFF-Q. So design is a very broad subject. You all probably come from a very diverse range of backgrounds, and you have a very diverse range of needs, and you probably all want to build different things, and all these things require sort of different design techniques or different fabrication techniques in order to build the things. So different fabrication techniques often require different design methodologies. So today I'm going to go through some of the maybe common principles and also talk through some examples just to kind of show you how to fabricate certain devices, some MEMS devices and some other things. Because it's hard to design for something if you don't know how to build it. So an architect probably knows how to build a house. Well, not hands-on, but they know the principles behind it. But they couldn't design for a builder to build a house if they themselves don't know how a house is actually built. So I'm going to go through some examples, and then I'm going to go through some mask making. Probably 90% of the devices that are made in the facility require some sort of, they use photolithography, so they need a photolithographic mask. And a mask is basically something that we shine UV light through in order to transfer pattern onto a substrate. Okay. So I'll go through a general sort of design process overview, and then we'll look at some of the software. And I think ideally, if we were going to do design, we would speak to individuals who have a specific need, and we would sit down and we'd go through the software with them, and we'd train them how to use a specific piece of software. If we had a day, we could probably put on a workshop where we had a whole day just for design, and we'd actually go through some examples and design some things. But in this 45 minutes, we don't really have that time. So then I'll go through the mask writing, and then we'll go through some of the examples there. So as I mentioned, you guys have all got different backgrounds, and that's the same with all our clients. Historically, we've had clients doing all sorts of different applications. These are probably just some of them that we do. So we want to be able to design these. And when I'm talking about design today, I'm talking about sort of planar technologies, where we use a clean room, where we use photolithography, etching, deposition, and we do cycles of these different processes in order to build up a device. I mean, we do have other capabilities. We've got 3D capabilities as well. We've got two-photon lithography. We've got other 3D printers that we can use to make 3D structures. And we might touch on some of that today, but mainly this is about planar type technologies. Okay, so a general flow would be you might do some kind of modeling. So when you come to us, you normally have some idea of what it is that you want to do. You want to prove a concept, or you might want to measure something, or do some sort of technique. Some of our clients will come to us and have already done some kind of modeling on a structure that they want to build. Other clients just maybe have a function that they want to perform, and they want to talk to us about it. So we do have modeling software, but where we come in is from the sort of consultation point here. So you come to us with an idea, and then that's where you sit down with us, and we talk through your project with you, and then we go through some ideas of some of the fabrication techniques you can do, and then that leads on to the design as well. And ultimately what we want to get to is a point where we do a layout. And basically a layout is just a pattern that we're going to put on a photolithography mask, and we might have one, or we might have 2 or 3 or 4 masks in order to build up a particular device. Then we're going to generate the lithographic masks, and then we're going to fabricate the device. We'll go through that cycle of photolithography, deposition, and etching. And then at the end, we do some kind of packaging if required. So it might be the device needs to connect to the outside world, or it needs to be put in some sort of package, needs to be hermetically sealed, whatever that needs to be. And then at the very end, you want to know if this thing that you've made spent months making actually works. So we need to do some form of test at the end and make sure it works. Okay, so as James said, we're there as a sort of consultancy as well, and you'll come to us with an idea, and you'll have your main idea, but maybe a few other ideas that go with that. But the idea, for example, you might come to us with a time machine, and you have this concept in your head, and it's very fixed. You want a DeLorean, but then over time, after speaking to us, you actually end up with a TARDIS. So it still does time travel, but it doesn't look like what you wanted it to originally. Okay, so things to consider. There's many, many things to consider, but when you think about it, once you've spoken to us, we need to start considering things like how wide, how thick, how thin, whatever the layer needs to be, the type of patterning they're going to do. You're going to do photolithography, which is quick, it's easy, but it only goes down to sort of 1 micron, 2 microns. If you need to go smaller than that, there's the UQ have just bought an electron beam lithography system, so, or 2 even. So it's another option you can do, but often these techniques are much slower. Then there's 2-photon lithography, which is a nanoscribe system I mentioned that can go smaller, much smaller than a micron, but again is much slower. And then you want to consider the materials that you're going to use, what's the function the device has got to perform, what environment it's going to perform that function in. And all these things help determine the materials you use and also the techniques, the fabrication techniques that you're going to perform. And then also the combination materials, because if you're going to perform a process in one particular material, if there's another material there, it has to be able to withstand that process as well. So there's many things to consider. So software, ANFF has what's called the Design House, and we host a bunch of expensive software packages. Some of them we don't use, some of them we use every day. So we've got things like Synopsys, and that's really a semiconductor package for doing simulation modeling right through to design of an integrated circuit. And that's not what we do. We don't do that kind of solid-state electronics here. But there are other nodes that touch on that. Griffith in particular, I think, do, but I don't know if they use Synopsys. Coventor and IntelliSense, they both do MEMS modeling and MEMS simulation and MEMS design and layout. We do use some of the IntelliSense package for our etching simulation. But the main one that we use is Tanner EDA. It shows Mentor Graphics because they bought Tanner EDA. And they do a software package called LEdit that allows us to do quick and simple layouts in order to develop photolithographic masks. So LEdit, it allows us to do, in particular, you can do 3D modeling, you can do simulation, but generally what we tend to use it for is just the layout down here. So we'll talk through that a little bit in a minute. And then IntelliSense, which is again another suite of tools here. So we can do schematic capture, which we tend not to do. It's got Blueprint, so we can do layout with this, but I prefer LEdit. We have this clean room modeling flow design here, which has got the etch modeling. So I'll maybe touch on that in the next slide. So when we do some of our etching, we can do wet etching, we can do dry etching, and you can go through different iterations in order to try and model, the end result, or to achieve the end result. But we can do some modeling up front, and it saves a lot of time. You can just do it at the desk, and we can show you how to do that. So Design House, it's actually hosted at Monash University, all the software there, but we have some packages installed locally in our workstations, and you can access these packages through us. But later on this year, they're going to set up as a cloud-based system. So if you need to access any of these packages later on in the year, you can just log in from your own PC. So all the number crunching is done down at Monash, and you basically just see it on your screen. So that will be quite useful. So some layout editors, so we've got LEdit, which is my preference, and I think some of my colleagues' preference as well, in order for doing layout. Blueprint, which is part of IntelliSense, I mentioned. There's also Layout Editor, which is a freebie. You can just download that from the web, and you can use that for doing layouts. And also there's one called K-Layout, which is another freebie as well, but it can't do circles for some reason. A lot of our clients use Autocad for layouts, which is probably okay if you're just doing a single mask. If you're doing many, many masks, then it gets a bit cumbersome, and we also have some issues when it comes to writing the masks. Some of these issues are formed from, basically our mask writer works on writing polygons. So a polygon is just an enclosed structure here, so it's got 4 vertices. So here, if we draw a polygon but we don't enclose it, and you might do that on AutoCAD and you don't realize you've not enclosed it because it looks enclosed, and then when we go to write it, it doesn't work. So what the mask writer just sees this as a single line, and it's infinitely thin and just doesn't print it. And the same for this as well. When you've got 2 overlapping lines, it's not an enclosed polygon, so it doesn't work. So sometimes we get designs sent from people, and they've spent a month, 2 months making this design that's got 1 million, 2 million vertices on it, and they're all, all these polygons are open, and we can't convert it. We have to go back to them and say, sorry, we can't print your design. So that's another reason why we don't like AutoCAD for making these kind of things. It's good for 3D stuff, but for 2D stuff, it's not too good. So for L-Edit, we can do sort of hierarchical design. And if you spend a bit of time up front of figuring out what you want to do with your design, how you're going to lay it out, then you can make a design that's easy just to print your masks off from that at the end. And also it means any future updates are very easy. If you need to go back and make a change to your design, if you use this sort of format for your design, then it makes it a lot simpler to change later on. So essentially, you design simple elements down the bottom, rectangles, circles, squares, whatever down here, and you can instance these up into higher levels here, and then up to arrays of much more complex shapes up here. So you can start off with something very simple and just quickly turn it into a very complicated design in a large array, and then you can print out your masks from these different from the top layer. So you can also, as well as defining different cells, you can define layers, and each of these layers represents a lithographic mask. So I've got 3 colors here representing the 3 masks here. So you might have 3 rectangles stacked on top of each other, and then instanced to a higher level, which form, an arm of a cantilever, and so on and so forth. It'll make more sense when I go through examples later on. So when it comes to mask writing, I'll just hand out a couple of masks, and you can just pass these round. If you want to just pass these back. Thank you. Oh, maybe when I'm on the example, yeah. So, most of the processes we do need some kind of lithographic mask, and you'll notice there's a brown side and a sort of shiny side on these masks. The brown side is actually the chrome side, and the other side is soda-lined glass. Okay, so we have a Heidelberg mask writer. So this works with a sort of UV laser or 405 nanometer diode laser. And it writes directly into photoresist that's on top of the mask. So we buy these masks in from Japan. They're loaded up, they're glass, loaded up with chrome and photoresist over the top. We put it on the system. We take our design and we write to the mask. So we can write up to 7-inch masks. So we tend to work with 7-inch and 5-inch masks. So we use a 7-inch mask when we're writing to a 6-inch wafer, And we use a 5-inch mask when we're writing to a 4-inch wafer. By wafer, I mean like silicon or glass, substrate, whatever, the substrate that we're going to build our device on. So what design file types does it accept? So it takes what's called GDS2, or Gerber Data Stream Information Interchange. So it stands for GDS2. It also takes DXF, but we prefer GDS2. And GDS2 is easily exported from LEdit and some of the other layout editors. It does take DXF. So DXF comes from Autocad. But DXF, if you do multiple layers, it just the mask writer just collapses them all together, so you can't print out individual masks. So we always just say GDS2. So if we ask you to put a design together and you send it to us, we always ask for the GDS2 file. So this is what a chrome masks looks like. So yours has been developed, so there's no photoresist on yours, but generally we get them with a layer of photoresist, and Elliot will go through later as to what photoresist is. There's an anti-reflective coat on top of it, so that's the brown layer that you see, which sits on top of the chrome here, and then we have soda lime glass or quartz. Okay. So what's the difference between soda lime and quartz? Well, soda lime's cheaper. It's the same glass that we use in windows, but it's not as flat as quartz, and it also doesn't transmit UV as well as quartz. So quartz can also transmit down to deep UV as well. So quartz is more expensive, so if you buy lithography blank masks from us, you'll see that they're much more expensive. But they do perform better. But for 99% of cases, a soda lime mask is fine for all the applications that we do. So what is mask writing? So if we've got a design, a polygon, so I've got an E over there, and the mask writer will write to that polygon. So what will happen is the laser will scan over. This is the cross-section of the mask, obviously, and then it just scans over there where the polygon is drawn, and where it's exposed with UV, it becomes soluble, and then we can develop it, and it removes the photoresist in that location. And then we can do an etch. So we develop it in a sort of basic solution. We chuck it in chrome etching, and then we remove the photoresist, and we're left with what you're passing around just now. So that mask is now ready to use in a photolithography process. Okay, so some other things to be aware of. There's a term chrome up, chrome down. So if you ask us to make you a mask, we'll say, do you want chrome up or chrome down? And what that means is, so if we've got this E here, and we print it, when we print it, the brown side is facing up on the mask writer, so it writes an E. So when you look down at it after it's developed, you'll see an E, which is fine. But then when you go and do photolithography in the clean room, you turn the mask upside down, and you shine light through from the other side because you want the chrome touching your substrate. So what you would get is actually the inverse of that appearing on your substrate. So normally what you want to do is you would ask us to do chrome down, and all that means is that we then mirror your design. So the design would just look like an inverse E, and then we'd write it. And by the time it gets to your substrate, it looks like a proper E at that point. Okay, other terms to know are Brightfield and Darkfield. So as I said, when it writes to where the polygon is. So that's what's called the Darkfield. It's called Darkfield because not much light goes through it. So you tend to draw some patterns on the substrate. It writes to it, but when you hold it up to light, it's quite dark. Whereas if you invert it and you do a Brightfield one, then you take off most of the chrome, so you hold it up to light. It looks quite bright, so it's Brightfield. Okay. There's an address grid on it. So there's two write modes on the mask writer, and it has different address grids depending on the write mode they use. So down to 20 nanometer for the mode 1 head and 100 nanometer for the mode 3 head. It just means that you can get smoother lines of the mode 1 head. But again, 90%, 95% of our masks that are written use the mode 3. So the difference between the two modes is that with the mode 1 head, you can write down to about 1 micron feature size, maybe a little less, whereas the mode 3 one, you can only write down to about 2.5 microns maximum. Okay. And then also the write area is different between the two as well. So I'm showing a mask sitting on top of a wafer. So that's a 7-inch mask sitting on top of a 6-inch wafer, and a 5-inch mask sitting on top of, sorry, not the mask, but the write area. Sorry, this is the available write area on mode 3 on top of a 6-inch wafer. So you can't write to a full 6-inch wafer. So if you want your design to encompass the full 6-inch wafer, we can't quite do that. You can see we can do most of it. So we can write 150 millimeters in X and 125 millimeters in Y. And then on mode 1, which allows you to get down to 1 micron resolution, we can do 90 by 90 millimeter. And whereas a 4-inch wafer is 100 millimeter diameter. Okay, so another major difference between the two is the write speed. So if you do want to write a 1 micron feature across a 4-inch wafer or a 90 millimeter square, it could take up to 135 hours. I mean, it wouldn't take that long, but it maybe take 30 or 40 hours, depending on what the design is. Whereas compared to mode 3, it can take about 3 hours to write a design. So that's another reason why people want to use the mode 3 option of the system. Okay. So with the, also just mention the address grid. When you are doing your design, you can also set up the manufacturing grid. So that's the grid that's used within your design. So I think by default it might be set to 1 micron. I'm not sure. So if you're drawing circles, you need to make sure you use a suitably small manufacturing grid. And we can show you all these things when you actually come to do the software, and we can train you up on how to do the software. Okay, so the best way to kind of go through the design and the kind of give you an overview of the fabrication techniques available is just to go through an example. So this is one I did. I actually did this one down at Melbourne. Somebody wanted a cantilever. So they wanted to characterize bubbles down here. So they wanted to suspend bubbles from a cantilever. So and they wanted to do it on a confocal system. So they have an AFM on top of a confocal microscope, so that they use the confocal microscope to do a 3D stack of this, and then also in conjunction with using the AFM to measure the forces between the two. So they knew with this setup they can measure the gap between the bubbles and also the forces applied. So it allowed them to sort of progress their research. So they needed these cantilevers, and you can buy cantilevers off the shelf from suppliers that are sort of like this, but they had specific requirements for the spring constant for the cantilever. So some of the features were, the minimum feature size is 50 microns, so they weren't particularly small, and the materials used, silicon oxide, and gold. So they needed gold on here in order to be able to trap the bubbles onto the end, and they also needed gold up here in order to be able to shine a laser off the back of it. And then they have to think, well, how many devices do I want? So they wanted quite a few because they're going to do a lot of experiments. So anyway, so we built it on a 4-inch wafer. So that gave them, I think, a couple of hundred devices from every single wafer. And then we have to think, well, what's it going to fit in? It's not going to be packaged, but it needs to fit into an AFM. So we go and measure an existing AFM cantilever and see what size we need in order to fit onto the AFM. So we do design, so sticking to the hierarchical design. So we start down at the bottom, we define some basic elements. So we've got the cantilever arm, which is a certain size. We've got the gold dot that the bubble is going to be suspended from. And then the body of the cantilever. These are not to scale, obviously. And then we also need to define how we're going to etch through the back as well. So we've got to define that as well. And because we're going to make different masks, we need to be able to align these to each other. So we've got to define alignment marks as well. Okay. So each color here represents a different layer. So we'll go into a different mask. And then, so we define the basic elements, and then we instance these to a higher level up here. And then these get arrayed into a bigger array up here. And it just means we then generate the masks, and if we need to make a change later on, say the cantilever is the wrong size, we've got the wrong spring constant, then all we have to do is change the size of that rectangle and then generate that mask that pertains to that again. And then we just need to, it takes 5 minutes to do that, and then the time to generate another mask. So you can go through design optimizations and modifications quickly. So this is the actual design. So again, so you can see the cantilever, the gold dot, the definition of the cantilever body and the back etch part as well. And then design a frame, because we're going to etch through a wafer in this particular one. If we don't have some kind of frame that holds the thing together, then when you etch it, they all just collapse and get sucked into the vacuum pump of the system. So you need to think of how it's the effect of the process that you're going to perform on the device as well. And then we generate, also we need to create a frame for all the devices to sit in, because if we don't mask this off when we do the etch step, then we're etching the whole wafer. If we don't put some sort of frame around here, then again it's all going to collapse inside the etch system. So then we've got our final layout here. So this is what it's going to look like at the end. So then we can generate 3 masks. So here's the 3 masks. This is what they look like after we've printed them off. There's not much to see on the first mask, because it's just 50 micron gold dots, or 50 micron dots that appear up here. And then this part here is what defines the top. So this is the top of the wafer. When we generate the device, this is the top, so it shows the cantilever arms there. And then from the back, we need to define how we're going to etch, because what we're going to do is we're going to etch the cantilevers from the top, and then we're going to etch all the way through the back. So we need a mask to define front and back. Okay. So going through the steps, so we start off with, we need what's called an SOI wafer, a silicon insulator wafer. So you can buy these. We generally don't make these. You buy these. So they make these by doing an oxygen implant into here and annealing in it. It forms an oxide layer in here. And the good thing about that is means we can just etch all the way through, and we can stop at the oxide layer. Okay, so I'm showing the cross-section of the device as it gets built here, and then how it looks from the bottom and how it looks from the top. So the first step is to spin on a photoresist on the top here. So every device starts off with photoresist spun onto the top, and then you can see that changes color over here. So we're going to use a negative resist, because this is going to be a lift-off process that we do. So you've got 2 options. You can evaporate gold or sputter gold on top of it and etch through photoresist mask, or you can do a lift-off process where you pattern the photoresist and evaporate gold on top, and then just lift it off, and it leaves the pattern there. The advantage of that is it tends not to cause shorts, and it's a bit cleaner. So we've put the mask on top, and then we expose UV through it. So because this is a negative resist, where UV, where it's exposed to UV, it cross-links. And then we develop, so where it's unexposed, it's soluble in the developer. And then we evaporate our gold on top of that. And because evaporation, and Kai will talk about it later, is very directional, it tends to cover high and low features. It tends not to cover walls. So it means that we can then remove this photoresist, and it'll take this gold away, but it'll leave this gold here. And then we've patterned our 50 micron dots onto the surface. Okay, so it's pretty simple. And then the next step, we want to define the actual cantilever shape. So then we go again. We spin resist. This time I'm going to use positive resist. So positive resist, where you expose it, it's going to become soluble in developer. So it will disappear where you've exposed it. So we put our mask on top. This is our second mask. And this is going to define the outline of the cantilevers here. And I've shown the alignment marks here, but really they're at the edge of the wafer. So again, we expose to UV, and it now becomes soluble in this part, this part, this part. And then we develop it, and we're now ready to do a DRAE. So we're going to define the shape of the cantilever now. So we put it in RIE, and we etch the silicon away. So again, because we've got the silicon oxide along here, we use that as our etch stop. So we can just etch down and over etch a little bit, and we know we won't go all the way through. So we stop here. So we've now defined the shape of our cantilever, as shown over here. So this is how it looks from the top. And we remove the photoresist. Okay, so that's the top. So it looks like a cantilever from the top now. And we need to do some processing in the back. So at the moment, it's still fairly useless because the arms are not free. So we need to etch from the back. So this is where we can do some further processing to pattern the back. But first of all, we've got to protect the front. So gold is quite soft. Because we're going to turn the wafer upside down, it's going to be sitting on a chuck. We don't want to scratch it, so we need to protect that side of it. And then we put our thick positive resist onto the bottom here. And then we're going to pattern it. So it shows here the mask is on the bottom. It's not actually. So we turn the wafer upside down. And then because of our mask aligner, we can align two patterns on the other side of the wafer. And so we can align this to the other side. And we go through our photolithographic step again. This now becomes soluble. We develop it, and we've now got a thick positive resist on here. So this is now ready to go into the DRIE, and we're going to etch through it. And because we've got our etch stop here, we can just hammer the etch right through until we get to this point here. So now you can see the cantilever is really beginning to take shape now. It's starting to look almost like a cantilever from the cross section. So we strip all the resists off. And now the last thing to do is really to get rid of this oxide. So sadly, the only way to get rid of the oxide is to perform hydrofluoric acid etch. So something we're going to be very careful with because it can kill you. But so when you do that release step, so we've now got our cantilevers. I've not shown the sort of lugs on here. So these are all suspended by thin pieces of silicon onto a frame. And then you can just put these down and just push them out and then take them away and use them in your application. Oh, sorry. No, you can't because you haven't spotted gold onto the back. So the last stage, so hopefully it's strong enough at this point that it will stand going into the spotter system or evaporation system, and then you can evaporate gold onto the back. Because in AFM, because there's a laser shining onto the back of it, it needs to be able to reflect that off and onto a photo detector. And now it's finished. So that's the final device. Looks like that. So because it's gold on it, it looks very pretty anyway, I thought. Okay, so the next example I've got is silicon nitride window. So this is something that we make for the synchrotron from time to time. So they want to be able to they want to be able to put things onto this very thin window. So the window can be down to 100 nanometers, 250 nanometers, depending what the requirement they have. So we can culture cells on top of this, or we can put other things, and then they can take that away and put it in their beamline. And they can do analysis of whatever it is that's on that window. So these are, again, these are fairly big structures, but it's just the technique's a little different in order to fabricate these. So again, we start off with a design. This one was generated from IntelliSense, where we did the etching and modeling on there, first of all, to get an idea of how it's going to look at the end of it, because we're going to do KOH etching, so it's wet etching. So last time we used the DRE to etch through. This time we're using wet etching, so KOH at temperature to etch through the silicon. So we generate our mask. So again, it's important to have a frame that the devices sit in, because you don't want to etch and then for the whole thing just to collapse at the end of it and just fall apart inside the wet bench. So in this case, because we're going to be doing KOH etching, we need to protect both sides with silicon nitride. So silicon nitride etches silicon quite readily, but it doesn't etch silicon nitride at all. So our job, first of all, is to pattern that silicon nitride and selectively etch some windows inside that silicon nitride mask. So again, we go through our photolithography step here. We apply our mask, expose through UV, and develop it, and then we're left with photoresist patterned onto the silicon nitride. And then we put it into the RIE. So we've got an RIE and a DRIE, and again, Kai will talk about the difference between the two later. So we etch through the silicon nitride. So we've exposed the silicon on one side only. The other side is protected. And then we can dump that whole thing into KOH, and we can etch all the way through the silicon. It takes, when I say quickly, but it'll take about 10 hours to go through, say, 500 microns. And it'll stop completely on the silicon nitride, leaving a window like that. So this is a very simple process, but it allows us to make some fairly useful devices. And in MEMS in industry, they use KOH etching quite a lot because it's very controllable. And we'll talk about KOH etching later on after lunch. So microfluidics, so Leanne later on is going to talk about microfluidics, but we do a lot of this, so I thought I should maybe just chuck this in. So this isn't a real device, this is something I just made up, where we've got a channel, like a Y shape, and some wells at the end of it. And what we want to do is generate a mold that we can cast PDMS off, polydimethylsiloxane, which is a clear silicone elastomer, that we can then build a microfluidic device out of. So what we want to do is generate a master, first of all. So in order to make that mold, often what we do is we make that mold out of SU8, which is an epoxy type photoresist. And we can make quite thick features. It can go up to about 1 millimeter roughly. So but it's still using standard photolithographic practices. So we're going to generate a mask from our design. So we start off with our individual feature, instance that up to a higher design, generate our mask, and then we start off with a bare silicon wafer, spin SU8 onto the top. So we have different series of resists. If you need high aspect ratio structures, then it's better to use this 2000 series. 3000 series has other benefits with regard to adhesion and things like that. But you can't do as high an aspect ratio structure. So we put our mask on again, expose. SU8 is a negative resist, so where we expose it, it's going to cross-link, and then it's going to remain like so. And then we cast PDMS on top of it, pull it off, and then it gets bonded to silicon and becomes a microfluidic device. Okay. Another thing is, so I keep talking about photolithography, but photolithography is limited on how small it can go. It can go down to about 1 micron, sort of minimum in size. But we do have other techniques. We've got the 2-photon lithography system, and UQ's now got electron beam lithography systems. But as I mentioned, electron beam lithography, although it can be quite quick depending on the pattern, if you want to do 10 nanometer structures all the way across 6-inch wafer, you'd be there for a long time. But sometimes you just need some small structures, and then a lot of the rest of the pattern is big structures. So a good thing to be able to do is to combine the two different techniques. So here, again, this isn't a real device. This is just an example. We've got some small features in here, and these could be in the 100 nanometer range. And then you've got standard lithography around about. So you can do standard lithography, generate your masks, go through the lithographic process, and then you can spin coat another layer on top of that, and do whether you can do EBL or you can go and do 2-photon lithography. So just as some background on, I keep mentioning the 2-photon lithography. So we've got a system called Nanoscribe, and it can do 3D type structures. What it does is it generates, it uses a 760 nanometer laser, which it won't cross-link photoresist, but because it focuses down to a small point here, it generates this 2-photon absorption down here. So in effect, you have a small voxel that's UV, and then you can move that voxel around in 3D space, and you can write 3D structures into a pattern. So you can write down to 100 nanometer minimum and write 3D structures. So potentially a device might look like this, where you might want to write these T structures, say, into a positive resist. So you use standard lithography techniques to write these kind of structures over here. And then maybe here you want to use Nanoscribe to write some smaller 3D or 2.5D type structures here. And then maybe you can electroplate up through them. So you can create some novel structures combining the two lithography techniques together. There's not one sort of software environment that allows you to do it. So the only way to do is to go through your normal lithography design process here in order to do the photolithography part, and then to do 3D, you need to just sort of fudge the two and get the two to align together. So you just need to understand your design, understand the dimensions, and make sure that the two overlay each other. Okay, that's all I've got to say just now. So I did it with a minute to spare.